Morning. So, if you just, before we get started today, this is what we're going to do, right? You can see on your notes, we're going to cover the next couple of pages today. So we're going to start with, these are sort of applications of differential equations, okay? Next time we're going to get on to what you do if you can't actually solve a differential equation. But today we're going to look at some applications. So the first one is population growth. We'll come back to this in a sec. The second one is pretty cool. It has a cool name. It's called Newton's law of cooling, right? And it's about how, you know, if you put a hot thing in a cold room, right, it's going to cool down, and this will sort of predict how quickly things cool down. So there's lots of applications of this. So that's the second thing we're going to do. We're going to do population growth first. But just to sort of convince you that this actually is quite a cool thing, right, I got some stuff with me today. So this dial is actually a thermometer, right? Tells me the temperature of the lecture theatre, which is apparently 22, right? It's B-well temperature. You can see that there. Okay, so it's apparently 22 and about 65% humidity in here at the moment. Or maybe it's slightly warmer, maybe it's 23, okay? What else I have is a cup of, like I can't tip it because it's got water in it. I can sort of tip it a bit, right? It's a Keep cup of coffee, right? Got hot coffee in it. Actually, it doesn't have hot coffee in it, it's just got hot water in it, but right? And I got this, okay, which is a laser thermometer. So, I just want to measure the temperature of this. I don't know if you, let me just show you, right? See that number? About 70, 69, 70 degrees. I measure it this way, I get 70. I get 70 degrees, okay? So this water is 70 degrees at the moment in a 23-degree room, okay? And the time is currently 9:12. Okay, so the temperature was 70 degrees, and the ambient temperature of the room, I'll call that TA, is 23 degrees, okay? So there's a measurement that we just took, right? This is called science. So what we'll do is we'll come back later in the lecture, we'll take some more measurements and see if we can actually use, right, as an example today, we'll try and use Newton's law of cooling to predict how quickly this water is going to cool down. So I'm going to leave it here and try not to knock it over and scold myself. All right, I'm going to put my piece of paper with the data on it over here. All right, and we'll come back to that later. So what we've got to do is we're going to get through this first, but even before we do that, right, you can head over here and we'll just try and remember some of the stuff we did last time, okay? So we started talking about differential equations last time, and what we learned was actually something pretty neat, that we can solve quite a few neat DEs, right? The ones that we learned how to solve are called separable DEs, okay? So here's a minute to have a think about this question, okay? Put your answers in, and we'll see what you can remember from last time. Okay, 10 seconds. Answers in. All right, let's have a look what everybody thinks. Okay, a reasonable split. A lot of people going for C. What does C say? C says that 1 and 3 are separable but not 2. Right, so A says not 3, B says not 1, and C says not 2. D says they're all separable. That's a fairly even split. So let me give you a little bit of time to talk about it. Okay, I'll reset this. Okay, let's say here's a minute and a half to have a chat about it. Okay, answers in again, and we'll see what everyone thought. Okay, answers in again, right? Don't be afraid to change your answer. Don't be afraid to stick with what you had before. Let's have a look. Okay, so most people switching to C. Let's have a look. This is clearly separable because you could divide the x squared over here and have x, or sorry, divide the cos y over here, have x squared on this side, cos y on that side. This one is also separable because you could stick the x on this side by dividing by x. So you have y's on this side, x's on this side. This one here, you could get the y on the left by subtracting it, but that's not the rules, right? The rules say it must be a function of x times a function of y. It must be something like this. dy dx equals some function of x times some function of y. This is a function of x plus a function of y, so it is in fact not separable. Very good. So at present, right, we have no way of solving this differential equation. It looks very simple, but we cannot solve it. In fact, it is reasonably simple and it is possible to solve this, right? It's kind of the next most difficult set of DEs, right? So we've done separable DEs. We could look at some slightly more general first order DEs that are not separable. This would fall into that category. And it is possible to solve them, but we're not going to do that in this course, right? We just want to focus on just getting the basics down, solving some kind of DEs. So you will come back to these kind of differential equations in another course, say Mathematics 1A or something. All right, here is another one. Let me give you a minute. Okay, this one says, once, you might need some paper for this one. Once you've separated, let me give you another minute. I already wasted 10 of your seconds. Once you've separated this one out, this is separable. Once you separate it out, what do you actually have to integrate? Okay, so you may find it useful to write something down. Right, you can do it in your head, but it's easier to just scribble it down. This one is non-trivial. You have to think carefully about this one. All right, 10 seconds. Answers in. There aren't very many answers so far. If you're not sure, just take a guess. Take the one that looks like it's the least wrong. That's my advice. All right, we have fewer responses than last time, but this is a harder question, so I'll chalk that up to people not being sure. Okay, so A and D look like the most popular responses. Not very many for C, and not so many for B and E either. All right, although they're not too bad. It's fairly even. All right, let me give you another minute. Okay. I'll give you a minute and a half to chat about it again, okay? And then answers in. If you actually manage to separate it out, right, on some paper, show the person next to you. They'll have to believe you if it's correct. Okay, answers in. Let's have a look. Okay, so a lot of people still going for actually almost exactly the same. I think maybe C has gone up a bit, but the rest of them, the ratio is more or less the same. Let's have a look, right? What we have to do to actually calculate it, to actually solve this problem is separate this out, right? We've got to separate it. That's the only way to solve it. But we can immediately rule out a few, right? When you separate the DEs, the whole point is that you're going to end up with something to do with y dy equals something to do with x dx, right? And then you integrate both sides. So these are all integrals of dy. So the thing we're looking for is this, right? What is on this side? Now, this one here is basically just you put plus the x on that side and you subtract this stuff on this side. But that's not how you separate it. You've got to get all the x stuff on this side and all the y stuff on this side. So whatever goes in here should have only y's, right? And whatever goes in here should have only x's. So that means I can say straight away that that's bogus, right? They can't be right. This says e to the x divided by y dy. It should be a y integral. It should have no x's in it. So sorry, all y'all 28 of you that answered D. And this one here, right, is also a bit suspicious. It says dy dx divided by y dy. So this thing here is also a sort of a function of x. It has two dy's in it, in fact. So that's a bit suspicious too. Okay, that's wrong. It's got to be one of these two. They're the only ones that only have y in them. Okay, so immediately I've got a 50-50 chance, right? Which is much better than a 1 in 5 chance. So to actually work it out, then you have to actually separate it. So let's take this, right? We got e to the x y dash minus x equals xy. So to separate this, first thing I'll do is put the x over here, right? And now you can factorize this, sorry, y plus 1 times x, right? xy plus x, pull the x out, and then I can put the y stuff on this side and the x stuff on this side. So putting the y stuff over here gives me this. Putting the x stuff over here gives me x e to the minus x dx. Right, dividing by e to the x and timesing by dx. So really, what we need to do is integrate this and integrate this. Well, this has got x's in it. That's something we need, but it's not what we're asking for in the question. Which one is this? It's e. So the y dash is really, so y dash is actually dy dx, right? That's this. And so the dx goes on this side, and the dy stays where it is, right? So it's a bit sneaky to write it as y dash. It's easier if you write it as dy dx, because then you can see the top part of the fraction is y, and the bottom part is x. This is actually a really nice question because you could solve this, right? If you think about all the stuff you've just learned about integration, integrate that, you get some kind of log. How would you integrate that? Anybody? Integration by parts, yeah. So you could actually solve this problem completely. Exercise, do that. Okay. All right, the rest we'll come back to in a little while after we've learned something. All right. So let's talk about population modeling. In fact, before we talk about population modeling, it's 25 past 9. Let's measure some water. It's still 23 degrees. Okay. Here's my water. Here's my thermometer. Okay, I don't know, can you see that? 53, right? Getting about 53. Let's write that down. So at T, so what time is it? It's 09:20, it's actually 26 now. So how many minutes between here and here? 14. So 14 minutes after we started. The temperature, what did I just say? 53? I thought I said 59. Oh, no, okay, I believe you. 53. Okay. So this is enough, well, we're going to learn about this in a minute, but this should be enough data, okay, to solve the relevant differential equation and get a particular solution so we could actually predict the temperature of this thing later. God, I hope this works. Okay. All right, so population growth. This is a really nice example of differential equations because it's important, and some of the models we have work very well. The one we're going to learn about today is not terribly good in the sort of overall, but it is a nice example of how this sort of stuff goes. And it's something that people are very interested in modeling, right? In biology, populations of bacteria or populations of some particular thing out in the wild, or even in like socioeconomics, populations of countries and certain demographics and so on. Okay, so one easy, if I asked you how do you think the population changes of some particular, of some particular population, how does it grow, right? A sensible suggestion is to say that it grows, the rate at which it grows is proportional to the actual current population. So the bigger the population, the faster it grows. The smaller the population, the slower it grows. That makes sense, right? That seems like a reasonable assumption. Actually works quite well as long as populations are relatively small. Once they get too big, there's a bit of a problem, right? Because they would start growing faster and faster and faster. Okay? Eventually, if that happened, you'd run out of food and water and you'd run out of space and so on. So let's not worry about what happens when we push that boundary. Let's just say that it's a reasonable assumption to make. So this gives us a differential equation, right? dp dt, the rate of change of population, is some constant times the actual population, right? So if the population is big, this rate of change is big. If the population is small, this rate of change is small. Okay, now this differential equation looks pretty easy, and in fact it is pretty easy. It's separable, right? The right-hand side is a function of p times a function of t. There's the function of p, right? And the function of t is just a constant. So you could actually solve this pretty easily, right? You could almost just see the solution by looking at it. I'm just about, if you want to solve it without knowing the answer, do so now. Okay, I'm going to ruin it for you. Here's the answer, right? It's very easy to, in fact, check this is the answer, right? Once you've got it, you can easily check it. Just take dp dt. The k comes down because this is an exponential, and you get k times this, which is k times p. So it's definitely a solution, right? It's the general solution. So a is just some constant, and k is the number from here. So k is some fixed number. You know what k is, comes from the model. But a is your constant, arbitrary constant. Okay, so this gives you exponential growth. All right, so how would you actually, how can you actually model things using exponential growth? Let's have a look. Okay, so what we've got here is the rate of growth of a population is 2% per year. Okay, so let's actually solve this. Let's actually solve the DE now, right, from scratch, and see that we actually get this answer. Okay, so the DE is p dashed equals 0.02 p of t. So that's 2% of the population, right? 0.02 of p. Right, that's how fast it's growing. Okay, so this is separable. What we can do is we can divide by p. Right, remember this is dp dt. So we can keep the dp on this side, and we can put the dt on this side. Right? Don't worry that I've written p dash of t and p of t. I'm just going to suppress that. I'm just going to call it p. Right? T is just the variable, but this is really dp dt equals 0.02 times p. Okay, so there's our separated dE. Now we just have to integrate it. Right? Well, this is easy. This is log. Right? And this is easy. This is 0.02 times t plus a constant. And so p is, you just take exponentials, right? It's exp of 0.02 t plus c. Or if you don't like it like that, you can write it as e to the 0.02 t plus c. Okay, and in fact, you can split it up using the rules of exponentials. You can write this as e to the this times e to the that, right? E to the c, e to the 0.02t. That's how indices work, right? You would add these two things together, which is what you've got here. So let's just call this thing a, right? Let's just c is a constant, right? Arbitrary constant. So e to the c is just a different arbitrary constant, still arbitrary. So let's just call this a. So this is a e to the 0.02t. So that's how you. I mean, that's exactly as the same as the general case, right? It's just that we actually have a number here, 0.02, whereas in that general case, in the discussion at the top there, it's just a k, right? But you see the solution is a e to the kt. Here the solution is a e to the that is k, right? 0.02t. So if we had an initial condition, right? We don't have any initial conditions here, so all we can write down is the general solution. If we had an initial condition, we could write down a particular solution.
So is k just the proportion of growth?
So k is the constant of proportionality. It tells you how the percentage of growth each year. Yeah, that's exactly what k does, right? It gives you the factor. I say it depends on the size of the population. K tells you how it depends, right? Okay, so note, right, here's an interesting fact. If we know P of 0, right, so this is the initial population, right, let's say P of 0 is some number. I'm going to call it P naught, right? So this means P at t equals 0, and this is a number that I have called P sub 0. So P with a little 0 at the bottom, some number like 10, right? So if we know this number, right, then if we put this into the equation we get P naught, which is this thing evaluated at 0, equals A times e to the this times 0, which is A, because that's 1. And so P is actually the initial population times e to the 0.02t. So it's actually easy to get a particular solution, right? And if you have an initial condition, we know that you can get a particular solution, not just a general solution. And it turns out when you have exponential growth that the particular solution is, right, this number, the A, the constant, is actually just the initial population. That's how it works out. Okay, so this is actually a nice model. So you can see the problem with this model, of course, is that here is a picture of the solution, right? Here's the initial population here, okay, and it looks like this, right? This is P equals P naught e to the something times t, where k is positive. Okay, and it's just going to keep going up and up and up like that, okay, which is problematic, okay, to say the least. It's fine down here, and it actually does model populations quite well down here, but over here, there's a problem, okay, because say you had some rabbits in a field, they actually would multiply like this, but after a while, that field would be so full of rabbit corpses that the rabbits wouldn't even be able to move, right? They would just be like knee-deep in dead rabbits. And so this is not going to work, right? Something's going to stop this growth. So there are more sophisticated models. I don't know, maybe you've seen them, maybe some of you have seen them before. There's a model called the logistic model. Has anybody seen that before? Anybody heard of that? A few people? Who's never heard of that? Doesn't matter. It's just a model, right? Another slightly more sophisticated model that starts out like this, but then counters for the fact that you can't just grow unbounded. Okay, so here's a couple of things for you to think about. Okay, I'll give you a minute to think about it. Okay, 10 seconds. Answers in. You don't really have to do any calculations here. Just think about what that model is telling you. Let's have a look. Okay, almost everybody going for C. I don't think I'll give you a chance to talk about that. Let's just check whether that makes sense or not. So this would be saying the population is negative. That's junk, right? The population is positive. It's just going down. This is the number out the front of it, right? So if this is negative, then the whole thing is negative because the exponential is always positive. So that's the same as this, right? That would be saying that the initial population is negative. That's junk. This is saying t is less than 0, which is, well, junk. I mean, it's okay. It just means you started measuring before you said you were going to start measuring, but it doesn't change anything. I mean, it doesn't tell you which way the population is changing. You don't run t backwards. That's stupid. So it must be this one. And in fact, if you think about it, if this were negative, you would have something like p equals a e to the negative something or other times t. And these graphs look exactly like this, right? Right. They are exponentials. E to the negative x goes down like that. So yeah, absolutely. That's correct. All right. So here's another one. Okay, we've actually just talked about this a little bit. Maybe I shouldn't have told you the answer. Okay, here's a minute to have a think about it. Just check if you were paying attention. Okay, 10 seconds. Answers in. That's pretty much everyone, I think. Let's have a look. Okay, looks like everybody was paying attention because I just showed you before that if you set t equal to 0, this will go away, and you end up with the value of this at 0 is exactly equal to a. So absolutely, it gives you a. All right, one more. This one's slightly harder, okay? You might need a piece of paper for this one. Okay, so suppose you've got something that is going down, right? The population is decreasing, like some radioactive thing, okay? That's decaying, and you know the half-life. So this is the time at which the population is half of the initial population. This really happens for radioactive decay, okay? What does that tell you? Does it tell you anything? You don't know the initial amount that's there, you just know the half-life. One of the student exercises does have something about radioactive decay in it. All right, let's have a look. Okay, so a lot of people going for B, but there's also some, which will be this one. That's kind of a sensible pattern since the last one was A, but it doesn't mean that it's correct. This seems to me the most likely one, D, which a lot of people are going for as well. Let me give you a minute to chat about it, okay? I'll wipe that. Okay, I'll give you a minute to talk about it. And then put your answers in again. Don't be swayed by the fact that B was the most popular. That absolutely does not mean it's right. We saw that in the last example. Answers in. Let's have a look. I don't know that we're going to get much consensus here. What was it before? Most people were saying B, and now a lot of people saying D. Is that what happened? So I told you that you should not believe the fact that it's B just because it was the most popular answer, but let's find out what happens, okay? So suppose we know that, let's call the half-life lambda. So that's how much time until there's half of what there was before. So if P of 0 is whatever it is, we don't know that. If P of lambda is half of that, that's what we know, right? We don't know what P naught is. We don't know what that number is, right? It's however much we have at the beginning. But what we do know is that after lambda, we have this much, right? We still don't know how much that is, but we know it's half of that. So what does that tell you? Well, that tells you that if you put a lambda into this formula, right? So P of t is P naught e to the kt, right? That's what we know. We don't know what this number is, but that's the formula that we've got. Okay, so P of lambda must be P naught e to the k times lambda. Right? But we know that this is equal to half P naught. So in fact, it doesn't matter what the initial population is, right? Because this tells you that you can get this by taking logs, right? So lambda is 1 on k log of a half. Right? That tells you what k, oh, sorry. We don't care about what lambda is, we care about k. K is 1 on lambda log to the half. So this number you can get, right? Without needing to know the initial population, you can still get it. So that's kind of a neat thing, and this actually is how radioactive decay works, right? That's why measuring the half-life is such a useful thing. So in fact, you were all right at the beginning, but I suspect not for the right reason, given that you were so quick to change your minds, right? Don't be afraid to change your mind. Don't believe the popular vote, but also don't be afraid to stick to your guns. Just select the right answer, no problems. No, it doesn't matter if you select the right answer or not. Point is that you learned something. Okay. Notice also that one of these student exercises here, 3.3.2, it says it's about carbon dating, right? And it does have some stuff about half-life in there, so you actually can play with this idea if you do this student exercise. Okay. So let's have a look at the next application, Newton's law of cooling. What does this say? So Newton's law of cooling says that it's fairly reasonable suggestion that the rate at which something will cool is proportional to the difference in temperature between the thing and the surrounding, the room, the ambient temperature. So put something very hot in a very cold room, it will start to cool down very quickly. Put something warm in a just a little bit cool room, right? It will start to cool down, but slowly, right? Not as quickly, right? So the bigger the difference in temperature, the faster it will cool down, okay? So how do you write that? right? You write it like this. You say, where are the notes? Right, you say this. The rate of change of temperature with time, so T is the temperature, big T is the temperature, little t is the time. So the rate of change of temperature is some constant times the difference between the actual temperature and the ambient temperature, right? TA is the surrounding temperature. In our case, it was 23 degrees, right? That's the temperature of the room. Okay, so can you solve this dE? Well, absolutely you can. It's separable, right? TA is a constant. K is a constant. So this stuff here in the brackets is a function of T. Sorry. This stuff here in the brackets is a function of big T, right? And the K, let's say, is a function of little t. So we'll leave the K where it is and we'll put this stuff on the left, just like this, right? So you divide by this and you leave the K where it is. And then you integrate this with respect to big T and this with respect to little t. Okay, and it's fairly easy, right? Integrating this gives you log, right, just like this. And integrating this gives you kt plus a constant, right? And so then you can solve this equation here, right, just by taking exponential. So do x for both sides, and you get this equals this plus x of this, right? And so it gives you, and we'll just use the same trick as before, right? So it gives you this, right? T is the ambient temperature plus some constant times e to the kt. Sorry, I'm way off the screen here. Why didn't someone tell me? It's pointing to nothing. There. Right? So exercise for yourself, right? Just go through this calculation. I mean, we can do it. We can do it again in a minute. Well, yeah, no, I'll leave it for you. So just go through this calculation yourself, maybe cover this stuff up, start with the dE, and just convince yourself you can get to this solution. It's just a separable dE, right? Just like the ones very similar to the one we just saw. Okay, so there are two constants here, right? C and K. Now, C is the constant that comes from solving the dE. It's the arbitrary constant, right? K is part of the problem, but if you don't know what the problem is, you have to take some measurements. That's what we did a minute ago. So here's an example. Let's do this example, and then we'll try, and then we'll see if we can. We'll come back to our water in a minute. Okay, so this example says there's a roast turkey, and it comes out of the oven when its temperature is 85. Okay, so T at 0 is 85. Right, that's when it comes out of the oven. And the room is 22 degrees. So TA, the ambient temperature, is 22. Okay, so first thing is, if the temperature is 65 after half an hour, okay, that's some data. So let's write that down. T of 30 minutes is 65 degrees, right? And then the question is, what is T of 45? Right? How cool is it after 45 minutes? Okay, so let's write down what we know. Right? There's the solution. Oh man, I'm doing it again. Sorry. Okay, there's the solution. So this is 22 plus C e to the kt. Okay, so now what we know is that if we put a 0 in, we should get 85. So 85 is 22 plus C times e to the 0. Well, this is 1, right? So C is 85 minus 22, which is 63. Okay? In fact, it always works out like that, you see? C will be the difference between the initial temperature and the ambient temperature. Okay, so T is 22 plus 63 e to the kt. So that takes care of one constant, right? You can get it by knowing the initial temperature. Okay, how do you take care of the other constant? You use the data that you've got. This is why we took 2 measurements of the water before. So we know that T of 30 is 65. So let's put that information in. 65 is 22 plus 63 times e to the 30 times k. Solve that for k. Okay, so this tells us 65 minus 22 is 43. Divided by 63 is this. Take a log to get the 30k, and then divide by 30. This should be k. right? Whatever that number is. Hang on, I wrote it down. It is, oh, I didn't write it down. Okay, it's whatever that is. That's a number. Sorry, I don't know what it is. You've got a calculator, you can work it out. It doesn't matter. Okay, so if we want to know t of 45, right, well, all we have to do is plug it into this formula, right? 22 plus 63 times e to the k times 45. K is, where k is this, right? And so that's just a number. Just put it into your calculator and work it out. This one I wrote down. This one ends up being about 57 degrees. Okay? So the other part of the question is, when will it be 40 degrees? So this is the other way around, right? So t of what equals 40? Right? That's the other question. So now you have to solve for t. So you know big T, and you don't know little t, right? So solve for this. But we know k now, right? So this tells us that if you do 40 minus 22, which is 18, and you divide by 63, and you take a log, right, to get kt, and you do 1 on k, that will be t. Sorry, that's a little bit quick. Just go through that calculation a bit more slowly. I just rearrange this for t. Right, k is a number, whatever it is. If you put this into your calculator, you should end up with about 98 minutes. So the point is, if you've got, say, the initial temperature and one other measurement, you can get the c and the k, then you can do whatever you want. You've just got a formula, right? You can solve for big T if you know little t. You can solve for little t if you know big T. It's not a problem. Right? Let's try this out. Right? So this is contrived. I have no idea where this data came from. I think all these numbers are made up. Okay? Let's try it and see if it actually works. Okay? So here's our data from earlier. Right, let's write down our formula, just like we did just then. So we'll have T equals TA plus C e to the KT. Right? And then to get this, we'll use T of 0, we'll use T of 0 equals 70 degrees. So 70 equals 23 plus C e to the 0, that's a 1. So C is 47. Okay, so this tells us that T is 23 plus 47 e to the KT. Okay, now we need the K. Let's use this other data to get the K, right? We know that when this is 53, then T is 14. So we get 23 plus 47 e to the 14t. Sorry, 14 times k. T is 14. K is what we don't know. Okay, so we rearrange this, right? 53 minus 23 is 30. On 47 is e to the 14k. Take a log. Right, that's 14k like that. To get k, just divide by 14. That's k. Okay, does anybody know what that number is? Let's find out. So log of, what is it? 30 minus 47. 30 divided by 47 on 14. Okay, minus 0.321, say. Sorry, 0.0321. That's approximately k. So this tells us that t is 23 plus 47 e to the minus 0.0321t. All right, so there's our model. And now we just need to predict the temperature. So what time is it now? It's 56 past, or 57 past. We took our first measurement at 12 past. Okay, so if we want to measure, if we want to predict it for in 1 minute's time, that will be 45 minutes gone, right? That will be 45 minutes gone. So we want to know what is t of 45. Right? So t of 45 should be this. Okay, let's see if we can. So we'll take this, we'll times it by 45. Whoops, sorry. Right, we'll take this, we'll times it by 45. Okay, and now we'll take exp of that. Okay, so that's this bit. We times it by 47, and then we add 23. All right? And we should have 34.1. Okay? Here we go. Moment of truth. 34, yeah? That is not bad, right? That's not bad. So I tried this, so about 37. So the actual is about 37. So I tried this at home yesterday, and after 40 minutes, it was within a degree. And after about 30 minutes, it was pretty much within about half a degree. So that's not a bad result. I mean, of course, this water is slowly evaporating as it cools down. The temperature of this lecture theatre and the humidity are not really constant. But it sort of illustrates that, you know, this simple principle gives you a differential equation that's not that hard to solve, and it really does actually model the real world. Something just as simple as this, right? You don't have to do second, third year maths. You don't have to do 5 years of engineering. You can already see something, some model of the real world. As opposed to the population one, which is a little bit bogus, right? You have to work a little bit harder to see real-world populations. But here already you can see a DE that actually works. All right, so I'll see you tomorrow, and we'll learn about what to do when you can't solve a DE, right? Then what do you do? Okay, see you then.